If you look at the Omap architecture, it's in my opinion unique because it's a very clever composition of multiple engines. We call it the smart multi-core. What does it really mean? On the one hand, we have the CPUs like anybody else. We have a graphics engine, we have a display engine, we have a video engine. We also embedded two M3 cores, Cortex M3 cores, which are used very effectively to enable very sophisticated multimedia scenarios without overwhelming the main CPU with interrupts. We have a security engine. If you look at the combination of all those engines working together, it allows us to address those tasks while maintaining a very consistent user experience on the one hand and running it in very low power on the other hand. This unique combination is really what allows us to be so successful in the marketplace as we see today. When you talk about quad-core or dual-core, what you are really referring to is the number of CPUs in the device. But if you look at the number of cores in the device, it's many beyond the CPUs. We have two CPUs which are used for the Android or for the operating system and the applications. We have two CPUs which are used actually for the low-level embedded control. We have the graphics engine by itself is multiple engines today. There is the video engine, the display engine, and so on. So in my opinion, the question is really, what is the best balance or mixture between the different cores and how this actually delivers the best user experience? We believe in a very balanced approach, balance between the CPU performance, balance between the graphics performance, balance between the multimedia performance. And one more important point to emphasize, the question is also what can the software utilize? Meaning, let's say for the sake of exercise that we put 8 or 16 cores, is the software ready today to leverage this effectively? Is it actually adding any value to the end user experience? Many of the applications out there are single-threaded, which means that in reality they run only on one CPU. So therefore the question is, what is the right balance and also when? Because over time the market from a software point of view changes and will be able to utilize better more CPUs. So that's the balance. For the time being, our decision for Omap 5 has been to use the best CPUs in the industry, which are the Cortex A15, and to use two of those. Maybe last point is that this question is not unconstrained. You need to live within a thermal budget. You have a given battery and you have a given package, and therefore you are not able to dissipate too much energy, too much heat. And therefore the question is also, what's the best trade-off in fitting within this thermal budget? For the time being, dual A15 and the two Cortex A4s is the right answer. Video is critical, but we don't run it on the CPUs. We don't believe that that's the right place to do it. We believe it's not the best trade-off in respect to energy, performance, and user experience. We have a dedicated programmable video engine, which we call the IVA, which allows us to run video encode and decode at amazing performance with with negligible workload on the main CPU. So we offload this task to the IVA, leaving the Cortex CPUs available for user applications. So that's actually a very good example. The decision is not how many cores, the decision is where you run the code. And video is a classical example. It's by far better to run it on a optimized engine for video processing rather than on a standard CPU. There is a difference in the thermal envelope, in the thermal budget between a smartphone and a tablet, no doubt, that's correct. Nevertheless, for the time being, in both of them, I think that a dual Cortex A15 supported with those smaller Cortex engines gives us a much better trade-off. For the time being, my answer would be both in the smartphone and in the tablet, that's the right trade-off. Many years ago, when we decided for the first time to put a graphics engine in an application processor, what we had in front of us was gaming. This was the main motivation for graphics. But I think that we have learned over the time that that's not really necessarily the case. Today, user UI, sophisticated UI, are actually probably the more I would say, the driver for the graphics performance. Why? We are talking about larger and larger screens. Not only the local screens, but also the remote screens. Why? Because we see an HDMI cable, we see Wi-Fi display, so you are able to actually take this small device, but run or drive a very large display. Large display means more pixels, but large display also means higher degree of composition, meaning more layers one on top of the other. To give the rich experience of a UI with a high level of composition on a high resolution display, you need massive graphic resources. How do you differentiate in a market where there is a small set of suppliers of graphics engine? The answer to me is the SoC. In reality, if you look at the performance, it's not only determined by the graphics engine, it's the graphics engine within the SoC. I'll give you a classical example: memory bandwidth. Graphics engines consume significant bandwidth of memory. If you don't plan it correctly, if you not allow within your SoC the right level of concurrency in the accesses to the memories and the right bandwidth to memory, you are crippling this graphics engine. So the way we differentiate is in the system level rather than just the graphics engine itself. And this is why we are seeing different performance of the same graphics engine in different cell phones in the marketplace today.